Hello, testing, testing, 1, 2. Good morning to everyone. Welcome back. Today we will have the final quiz, and the plan for today is to finish the last topic, and then next week we will enter the last tutorial, and then revision, and then discussion of quiz, and then we will be off for finals. Okay. Okay. So before we start, I found one interesting video to show you. It's about thinking in studies. Huh? Yeah, let you see. Let you see. I cannot go from the start, so later we restart. Okay, let's start again. Understand or not? Understand? Don't understand? Where got thing is like where got thing you should direct translate to Chinese. Yeah. So it's like uh ，yeah，所以我哪里有思考，就是说，like he how to say he um so he wrote an essay, so he spent a lot of time working on an essay and then write about 5,000. He thought that he wrote very well, but the lecturer says, I don't know what you think. So he cannot like from the work he do, he cannot know what he think. Okay. So he was like being sarcastic. So he said Malaysian didn't think. Okay. So this apply to everyone who don't think. So who just want to finish the assignment, uh, didn't how to say have independent thinking. Okay. Get it? Everyone got it or not? Yeah, don't got it. Okay, never mind. Yeah. Okay. So who got it? Then make sure you think. Okay. Next. Okay, so today we go into the last lecture. Today we will talk about the Boolean algebra. So this is the very first thing we touch. Okay. So we did the propositional logic, set theory. Okay. These two theory have this algebra structure inside it. Okay. So what is Boolean algebra? So a Boolean algebra is a set B with two binary operation. Okay, we need to know how to combine the elements in the set. Okay, so there are two of them. One is we call a cup, and one is we call a cap. Okay, or sometimes we will write plus or minus, plus or multiply. Okay, then we must have two elements called 0 and 1. Okay, 0 and 1. And one unary operation, which we call the bar operation. Okay. So you must have these five elements, not elements, these five criteria, okay? Such that there are few rules to obey. So what's the use of 0? So if you cap any element with 0, you get back yourself. Or you cap every element with 1, you get back yourself. Okay, so this should be familiar to you. This is the identities laws. And what's the use of the bar operation? So so after taking bar, we will call it a complement of x. Okay. So if you cut with your complement of x, you get back the 1 identity. And then if you cap with the complement, you get 0. Okay. Next is associative laws. So if you cut 3 elements together, okay, it doesn't matter you cut on the right first or you cut on the left first. They are the same. And if you cap on the right and you cap on the left, you also get the same result. Okay, so these are the associative law. Next is if you cap two elements together, it's the same as you cap it in a different order. And similarly for cap. So this is the commutative law. And then next is the distributive law. If you do the cap and cap together, okay, it's the same as you cap the element first and then you cap it. So this is the distributive law. So one way to remember this distributive, you should remember as to open up the bracket in the multiplication. Okay, so what's Boolean algebra? So Boolean algebra is the one set with 5 criteria here. Okay, 2 operations to tell you how to combine 2 elements, and then 1 unary operation and the identity, 2 identities, 0 and 1. Okay, and then satisfying these 5 laws here. Okay, so this is not something strange. We have examples before from the very first few lecture. So the first one is the propositional logic. Okay, So not sure how many recalls what's the 0 in the propositional logic. Is the false statement. Okay. And then T1 is the true statement. Okay. And then you have different propositions in your set. Okay. And then two proposition you can combine with taking the disjunction or the conjunction. P or Q. P and Q. Okay. Hopefully you still remember. And then you can take the negation of the statement. Okay. Not P or not Q. Okay. And then remember we have these the long big tables. Okay. So the big tables contain 5 of these laws. Okay. So they are Boolean algebra. Okay. And second example is the set theory. Okay, set theory. So set theory, in set theory 0, we have 0 as the empty set. Okay. And 1 as the universal set. Okay. And then we have a different set. And 2 set, we can take the union. We also can take the intersection. Okay. And what's the bar operation here? We can take the complement of the set. Okay. And we also have the big tables, big set identities for the set theory, right? So these are all the law that satisfy the satisfied by the operation of set. Okay. And lastly, so last time we stopped at graph at trees relations, right? So surprisingly, lattice can also define a Boolean algebra. Okay. So in this case, given two uh, given two lattice point, okay, how do you generate another lattice point? What do you think? Given two lattice point, how do you generate another lattice point? So the hint will be lying inside the definition of lattice. So how do you generate another lattice point if you have two lattice point? Hmm? What's the definition of lattice? What greatest lobang? What? Why suddenly? Huh? Why? Yeah. So what's the definition of lattice? Huh? It's a pole set with every pair of elements has has uh has the greatest lower bound and no okay, yeah, lowest upper bound. Okay. So this means two pairs of these I can generate the greatest lower bound or the lowest upper bound. Okay. So this will become the operation. So for example, xi cup xj, we can take the greatest lower bound of xi and xj. Okay, so it is unique, right? Because there's only one greatest lower bound because it's the greatest one. And then si cup sj, we can take the lowest upper bound. And this is unique because it is the lowest one. Okay. You cannot have two lowest one. If there are two lowest one, which one is lower, right? So lowest means there's only one. Greatest means there's only one. Okay. Okay. So what's the 0 and 1 here? So 0 and 1 here, 0 will become the least element. And then 1 will become the greatest element. Okay. So how about defining bar operation? So the bar operation will be depend on x, and you need to satisfy the identities law. So the identity law is x or x is 1, and then x cup x bar is 0. So for any x, you need to find another x such that when you cup them together, you get the greatest element. Or when you cap them together, you get the least element. Okay. So you need to check all these. So it's not trivial. And you need to check that this criteria here will satisfy the 5 laws here. 1, 2, 3, 4, 5. Okay. I think textbook got it. Maybe you can check. If you're interested, you can find me. Okay. So this is your familiar table here. Boolean identities. So apparently, if you are Boolean algebra, you can satisfy all these identities, okay? Although just now we only list 5 laws, right? But from that 5 laws, we can derive that they have to satisfy all these identities here. Okay. So uh so this is what we call the abstract algebras, okay? So we don't care, we don't need to know the set, whether it's a proposition or a set theory. We just care about the structure, okay? As long as any algebra have the structure, they will satisfy this set of identities. Okay. So this is the any question? Any question? Start thinking. Yeah. Huh? Yep. Yep. Those like and cup. Huh? Oh, you mean this? You mean this? Oh, this just mean the we need 2 operation, right? 1 cup. Okay. So in this definition here, so a set we need to have 2 operation, cup or cap. Okay. So I'm now defining what is cup and cap in the lattice. Huh? Make sense? Huh? You mean this? What is the SI? Oh, how to get this? So you need to so given any how to say? So last time which one we think is a lattice? What's the lattice again? Any example of lattice? What's the example of lattice? I think one of them is this. I think this is lattice. Okay. So for example, the greatest element is this one, right? The least element is this. Okay. So this means that when x cup with x bar, you want to get the greatest element. And then the cup, did I use the, huh? How do we get the x bar? Yeah. 1 point. Yes, 1 point. That's right. That's right. Huh? Yeah. So I'm trying to show you. So let's see. So for example, we pick this x, right? Okay. So the question is which uh which point should be this x bar such that when you take the lowest upper bound, you will get the greatest element. Right? Okay. Makes sense. Is this a lattice? Is this a lattice? I think in your book say this is a lattice, right? Right. Is this a lattice? Okay, let's say this is a lattice. Hmm? So you can take x bar as this one, right? So when you take the lower bound of these 2 points here, you will get the greatest element. Understand? Make sense or not? Yeah, yeah, yeah. Can as long as you satisfy this equation here. Okay? Yeah, yeah. Okay, okay, okay. Yeah. Okay. So next, next. So next, we will talk about function. Okay. Talk about function. So next, let's look at a set just containing 0 and 1. Okay. So we'll talk about a function going from the tuple of B to B. Okay. So let Bn be the set containing a tuple of xi, where xi is in the set B. Okay. And this is the set of all possible n tuples of 0 and 1. Okay. And the variable that only can take 0 and 1, we'll call it a Boolean variable. Assume value only from B. Okay. And then a function that take in n values from B and generate one value in B is called the Boolean function. Okay. So a Boolean function will take n tuples of 0 or 1 and then just give you 0 or 1. Okay. Should I give you example? Okay, maybe I just give you example first. So for example, you see fxy, right? Okay. Let's say I define fxy to be xy. Okay. So when I evaluate f01, okay, two tuples, or we call it a what do we call it? Two ordered pairs. Okay. Ordered pairs of 0, 1, and then we get 0. Okay. So we only put in two values of 0 or 1, I just get one value of 0 or 1. Okay, so this is the Boolean function. Next, next is the Boolean expression. So Boolean expression in the variables of S1, S2 up to Sn are defined recursively as what we can put in the Boolean expression is 1, 0, 1, and the n variables. Okay. So first of all, these are all the Boolean expressions. And from this expression, we can build more expression. So we can take the complement, or we can multiply together, multiply two Boolean expression together, or we can add two Boolean expression together. Okay. So I'll start with the Boolean expression. Start with 0, 1, and the n variables. We can take the complement, or we can multiply, or we can add them together. Okay. So for example, we can take x or y, or we can take x plus y, x times y, or x times y plus 0, or x times y times 1, or a xy bar. Okay. So these are all Boolean expressions. Okay. So actually you can see that each Boolean expression here represent one Boolean function. Okay. So you can make this Boolean expression into a Boolean function. So we can make each Boolean expression into a Boolean function. Okay. So you can see that for this Boolean function, we can add them together. We can multiply them together. We also can take bar operation, right? So you can ask whether the Boolean algebras or Boolean functions form a Boolean algebra or not, right? Okay. Huh? Huh? Next. Okay. Very hot. Okay. So you can ask whether these Boolean function form a Boolean algebra or not. Okay. So it forms a Boolean algebra. So let's see how to define the Boolean algebra on the Boolean algebra, Boolean functions. Okay. Okay. So when are two Boolean function the same? Okay. So in an ordinary functions, so how do you know whether two functions are the same? Huh? How do you know two functions are the same? In normal function. Huh? So when you put in the same input, you get the same output. Okay. So this is how to check two functions are equal. Okay. So this is the same as the Boolean function. So if you input the same element in the domain, you get the same image. Okay. So they agree on the image. Belong to B. Okay. So for example here, if you look at this fz, equals to x plus y times z bar, and then g is xyz bar plus xy bar z bar plus x bar yz bar. Okay. So if you plot out the truth table, okay, and compare them, you should see the same output. Okay. That should be the same. Okay. You can try and plot it up. Although they might look different when you plot out the truth table, that should be the same. Okay. Another way to see it is this one. Maybe this will shed a bit of light for later. So try to put it here. Okay, so let's say we just plot the column for the F. Okay, so you can see that this column have 3 1s. Okay, and then it turns out that this 3 1 here is produced by these 3 terms here. Okay, you can try and check it out. Okay, size. You can try and check it out. For example, this term here, okay, is coming from x times y times z bar. Okay, and then this term here is x, y bar, z bar. Okay, they don't have y bar, so you need to create yourself. And then x bar, y, and z bar, you get 1. Okay, you should go and check it out. Okay, so we say that these two are equal, but actually there's a name for the G. So G is called the sum of product expansion of F. Okay, so this is in the section 12.2. You can see that in G, these are all products of variables and you're taking sum of them. Okay, but here is the product of sum. Okay, sum of products. Okay, okay, next definition. So when are two different, next we will discuss about when are two different Boolean expressions are equivalent. Okay. So for example, we have xy plus 0, and xy times 1. Okay, so these are all equivalent. Okay, so although their expression looks different, but they are the same. Okay, because this is using the Boolean identities, right? Okay, xy plus 0 is just xy. Xy times 1 is just xy. Okay, so these are when two Boolean expressions are equivalent. And then next, how do we take the complement of a Boolean function? How do we take a complement of a Boolean function? How do you take a complement of a Boolean function? How do you take a complement of a Boolean function? Huh? Last what? Say again. As expected. Oh, complement the expression. Yes. So you just take the complement of your expression, right? Okay. So if you don't have a picture on your mind, so maybe you can imagine one Boolean function. Then when you consider the complement of your function, you just take the complement of your expression. Okay. Okay, next. So after complement, we need to define the sum and product. So the sum here, we will call it a Boolean sum. And the product here, we will call the Boolean product. So how do you take the Boolean sum of two? Thank you. So we will have two Boolean function. How do you take the Boolean sum and the Boolean product? Hmm? How do you take the Boolean sum and the Boolean product? How do you take the sum and product? Huh? Huh? You also add out the expression again. Okay, so it's an easy definition. And to check that they actually satisfy the law is also not quite hard because they also, you verify them from the expression. Okay, but the expression itself is coming from the Boolean variable. Okay, so expression itself satisfy the Boolean algebras. So the function should also satisfy the Boolean algebra. You can check it. You can verify it. Okay. So next, we should recall a bit on the logic gate. So last time we briefly talked about this during the propositional logic. So Boolean algebra is used to model the circuitry of electronic devices. Okay. And the basic element in the circuit are the gate. Okay. So what kind of gate do we have? Do you remember? What kind of gate do we have? And or and negation. Okay. So these are the inverter gate. Okay. The OR gate or the AND gate. Right. Remember P become not P. Okay. Or inverter gate, OR gate, and AND gate. So you can see that last time I think we draw on the board. We have two different circuit but have the same expression. Okay. So you should understand that the circuit is not unique. Okay. So you can use different gate to build a same circuit. Okay. So the question here is, since you have different, you can build same circuit in different way. So which way is more efficient? Can you use the shortest way possible to build the circuit? So this will lead to our main topic today is a minimization of a circuit later. Okay. So you can see that the circuit can get more and more complicated. Okay. And there's one section in the book, 12.3.4, is about adders. You can read about it, but it won't be important for the exam. But you can read about it. I'm not sure what's the use of it, but you can read. Okay. Uh, any question or not? No? Maybe we'll take a break, 10 minutes, and then we'll come back for minimization of circuit. Hello. We come back at 9:55. Why a lot of you seems like disconnected from the class? Why disconnect? Wi-Fi not good. Signal not good. Some leave chat already. Leaves the chat room. Huh? Content too boring. I also feel like very boring. Huh? Huh? Yeah. Okay. 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 Who? Huh? I don't know. Huh? No joke. No joke. I put the video also not funny. Hi. Sad. Huh? No one understand one. Hi. Sad. Okay, never mind. So next is the minimization of circuit. Okay. So why do we want to minimize it? We want to increase the efficiency, or we want to reduce the cost. So next, you can see that there are two examples here, right? Okay. So if you look at the first circuit here, we use four gate to build it. So the final product is XYZ plus XY bar Z. Okay. But you can use distributivity to pull the Y and Y bar out. Okay. But what is Y plus Y bar? P or not P is tautology, is 1. Okay. So you get 1 times XZ, you get XZ. So actually you just need to build the gate XZ. XZ is what gate? What gate can you use? Two variable multiply together. So it's what gate? AND gate. Okay. So you just use one AND gate. You can replace the 4 logic gate here. Okay. So this is using the algebra to compute it. Okay. So before we get to the algorithm, so we need to introduce some terminology. So first we introduce is a literal. Okay. So what's a literal? So what's literal? So literal is a Boolean variable and its complement. Okay. So maybe you ask, why we want to call a new name for Boolean algebra? Okay. So because we want to differentiate x and x bar. Okay. So that's why we call it literal. So we want to consider the variable and its complement. Okay. We want to differentiate these two. And then the next one is what we call a mean term. Okay. So a mean term of the Boolean variables is a product of n literal. Okay. So a mean term for uh of the variables x1 to xn is the Boolean. Okay, not because can have different product. So it's a Boolean product of n literals. Okay. So for example, you have x, y, or xy bar, or xy bar z. Okay. So these are all mean term, minimum term. Okay. Yep. Ah, yes. 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 So all meaning like include all these. Okay. Either one is true. Okay. Okay. Can I cannot put n, cannot put n because this is not variable n complement, right? Either you are a variable, either you are complement. That's why we put n or here. Okay. And then if you consider a product of them, it will be the mean term. Okay. Minimum term and value term. Okay. Next. Next. Okay. Next, we're going to this K map here. Okay. So this is called the Carnot map. Okay. So what's a K map? So a K map for a Boolean function. Okay. So it's in the n variables consists of two n cells. Okay. So if you have n variable, you need to build two n cells where you put one in the cell if you have a mean term inside your expression. Okay. Okay, before going to the example, I need to tell another thing is the adjacent cell. So cells are adjacent if the mean terms they represent differ exactly in one literal. Okay. So let's see an example here. So let's say we want to build a K map for this function here. Xy bar plus x bar y plus x bar y bar. Okay. So how many mean terms here? Three mean terms here. Okay. And how many variable in the function? Two. Okay. So two variables, you need to have 2 to the power 2 cell. Make sense? Okay. So we have 4 cells here. Okay. Each cells here will represent a different mean term. Okay. So for example, first one we will have xy, and then second we will have xy bar, third we will have x bar y, and then fourth one we will have x bar y bar. Okay. And then so to build a K map for this function here, okay, we will need to have to put one in the cell that represent the mean term. Okay, so for example, we have x y bar here. Okay, so we need to put a 1 here. And then x bar y, we need to put a 1 here. And then x bar y bar, we need to put a 1 here. So in total, we have 3 ones in the cell. Okay, make sense? If you don't follow this, basically you will be lost for the next hour. Okay. Okay. Since this is the last lecture and you are not like holder anymore, not baby anymore, I won't care too much. So I'll just go past. If you don't follow, then I have no idea. Okay. Okay. So we have 3 ones here. Okay. So this is the care map. Okay. So you will see that these two are adjacent. Okay. So these two are adjacent because they are differ in y variable only. Okay. And then why these two are adjacent? Because they are differ in x. Okay. And then these two, why are they adjacent? They are differ in exactly y. Okay. And then these two, y adjacent, they are differ in x. Okay. Okay, next, we will use the K-map to build this K-map minimization method. Okay, so first, what we do is, given a function, okay, any function. So when we give a function, you should imagine a logic gate behind your mind. Okay, you use the logic gate to build this function. Okay, so we want to try to minimize the expression of the function before we build the logic gate. So first, you can build the care map like what we did just now. Okay, given a function, build one care map. Okay, the next one is you identify the largest possible blocks. Okay, so this block here is of the form 2m times 2n. Okay, or OMN. Okay, so meaning you can only form 1 times 1 block, 1 times 2 block, 2 times 1 block, or 2 times 2 block, 4 times 2 block, power of 2. Okay. So it's not allowed to build like 3 times 1. Okay. You cannot do this. Okay. So you can only build powers of 2 blocks to cover all the one inside your care map with the fewest block and the largest block. Okay. Use the fewest block and the largest block. And then min terms can be defined based on the block you have. Okay. Oh, I forget to pass the attendance. Don't sign for your friend because need to contact them for quiz if they don't come. Hello. Okay. Yeah. So okay. So for example, in two variables, okay, two variables, 2 to the power 2, you have 4 cells. Okay. So let's say we have this function here. Okay. Fx equal to xy. Okay. So there's only one min term here. Okay. So you put 1 in xy. Okay. Then you will circle the one with one block, with a block. But you can see that xy is the most simplified form. So we only left with xy. Okay. So let's say, for example, okay, for example, we have fx equal to xy plus x bar y. Okay. Then you will put 1 in xy and then put 1 in x bar y. Okay. Then a block you can form is a 1 times 2 block to cover all the ones here. Okay. So you can cover it by the 2 times 1 block here. And then you can see that you can simplify the sum here. Okay. So why? You can see one way is to see it from the algebra. So if you have these two min term here, you can see that uh, you can distribute the y. Okay. So when you add x and x bar together, you will get 1. Okay. 1 times y is 1. Okay. So that's why the adjacent here cell can be reduced to just y. Okay, this is the principle to simplify this circuit. You only need to know this principle. Adjacent cell, why they can combine? Because x plus x bar is 1. And they only differ in one literal, okay? That's why you can do the distribute law. Okay. So next one will be this. So what's this? This function is x bar y plus x bar y bar. Okay. So x bar y plus x bar y bar. You also can distribute the x bar. Okay. So that you can combine the y and y bar. Okay. So if you combine these two, you will get x bar. So you reduce, you reduce your min term by one literal. Okay. Make sense? Okay. So adjacent cell can reduce to one literal. Okay. And then the next one, this one is 4 min term here. So we got xy, xy bar, x bar y, and then x bar y bar. Okay. So if you have 4 of these, the claim is they reduce to to 0 literal. Okay, no literal, just become 1. Okay. Why become 1? Because one way to see is you add out all the possibilities. Okay, so it must happen. If you plot the truth table, you will see that they're equal. Okay, plot the truth table. Or second, you also can play this algebra game. Okay, so you can see that actually you can distribute y and y bar. You can distribute y and y bar. Okay, and then what you get is y plus y bar. You get 1 again. Okay, yeah. So there are different way you can see it. Okay. So you can see that when you combine more adjacent cell, the number of literal reduce more. Okay. Yeah. Okay. Okay. The next one is a bit not awkward, but a bit different here. Okay. Let's say we look at these three. Just now the Carnot map we look at x bar y, x bar y bar, and x y bar. Okay. How do we form the block? Okay. Can we form something like the Tetris? Huh? No, this is not allowed. Okay, because this is not in the form of 2 times n times 2 times 2 to the power m. Okay, because Tetris you cannot simplify. You only can simplify adjacent cell. For example, this one. Okay, but you can see that if you only simplify this block here, you haven't covered all the one. Okay, so you need to form another block. Okay. Okay, so now you need 2 blocks to cover all the 1. Okay, so the first block will reduce to y bar, and then the second block will reduce to x bar. Okay, so the sum of products here will just reduce to the sum of 2 1 literal. Okay, yeah. I just remind you this one will be in the exam. Okay. Next, in essence, blocks of 2 adjacent cells represent pairs of minterms that can be combined to a term of 1 literal. The block of all cells, all 4 cells represent a product of no literal. Okay, but this just only applies to 2 variables. Okay. Okay, so let's see in 3 variables what happened. Okay. So in 3 variables, how many cells do we have? Huh? 2 to the power 3 is how many? 8. Okay. So you got X cells, 8 cell, 8 cell here. So how many ways to combine 4 cells in this case? How many ways to combine 4 cells in a 2 to the power m, 2 power n form? Okay. So you can do 2 times 2, okay? Or you can do 4 times 1. Okay. So either you can do like this, or you can do like this. So let's see the example. So for example, you can combine these 2 elements here, okay? So it doesn't become a product of 1 literal, but it reduced by 1, right? Because you can combine the x and x bar. For example, these two, yeah, why these two can combine? Okay, actually these two are adjacent. If you look closely, here is yz, here is y bar z. So they differ in exactly 1 literal. Okay, so the order here is very important. So you cannot place y bar z here. Okay, you cannot place y bar z here because these two are not adjacent. How many literal they differ? 2. Y is different, Z is also different. Okay, so that's why we put Y bar, Z bar here. Okay, so that means these two are adjacent. Y, Z bar and Y bar, Z bar is adjacent. And then Y bar, Z bar and Y bar, Z is adjacent. And then Y bar, Z and YZ are adjacent. Okay, so you cannot simply place your variable here. Otherwise, your KMac wouldn't work. Okay, so make sure you put the right adjacent cells. Okay, so you can see that if you include more blocks, you cancel more literals here. Okay, so 3 literals just left with 1 literal. And then here is another way to combine 4 cells. And then if you combine all the cells, you will get everything. You get 1. Okay, yeah. Okay, before go to the next bit, we need to introduce these 3 concept here. Implicant. Okay, so just now, when we say we combine this into a simplified mean term, actually these terms are called implicants. Okay, so these are the products of literal correspond to a block of all ones in the KMac. So this guy we call implicants. The simplified form we call it implicant. Okay, so they are implied by the blocks. Okay, implicant. So they are a simplified form of the blocks of 1. We call it an implicant. Okay. And then next, we will call the. Should I see example and then introduce? Example first. Okay lah. Try and first twist it around this time. Huh? Work so boring. Sometimes boss also tell you works or you also don't understand how. Boss give me example. Okay, don't know lah. Never mind. Okay, just switch another way. See how it goes. Okay, so okay. So let's see example. Okay, see example. We want to use a KMap to minimize this sum of products of 3 literals. Okay, so first what you do is you see these these min terms, right? Functions. So you produce a KMap for 4 of them. Okay, so first one you have 4 terms, 4 min terms. So you have 4 ones here. And then B, you have 5 min terms. So you put the right, 5 ones in the right place. And then you have 7 7 minterms for part C, and then you have 4 minterms for the part D. Okay. And then what you do is you form the largest 2 to the power n and 2 to the power n blocks. Okay. Okay, after you form it, you need to try to produce the implicant. Okay. So for example, in part A, okay, let's look at part A, right? So here, there's only one block. Okay, so this is the most simplified form. Okay. How about this one? What's the implicant that correspond to this block here? Huh? S, Z, bar. Okay, because they differ in Y and Y. So Y and Y bar combine to one. And then the next one is what? Y bar, Z bar. Okay. So the answer will be X bar, YZ plus XZ bar plus Y bar, Z bar. Okay. So these 4 terms here will get unified to XZ bar plus Y bar, Z bar plus X bar, YZ. Okay. How about B? Okay. So what's the implicant correspond to this 2 times 2 blocks? Ah, Y bar, just Y bar. Huh? Right? Because your Z bar and Z can combine, your X and X bar can combine. Okay? So you're just left with Y bar. So if I want to remind you again, so these 4 terms are actually Y bar Z plus X bar plus X Z. Okay? So first you can combine your Z first, right? Mm, okay, I didn't. I do something wrong. Yep. Okay. So should be like this. Plus X bar Y bar times Z bar pi Z. Okay. So here become 1, here become 1. And then you can see that you can factorize X bar again. Okay. And then you get Y bar. Okay. And then you can see that there's another block here. Okay. So this is a S bar Y bar Z and S bar YZ. Okay. So when you combine these 2 blocks here, what do you get? You get X bar Z. Yes. So in the end, you were left with the 5 sum of term here become just 2. Okay. Okay, similarly, you can do for C. Okay. D is more interesting here. Okay. D, you have 4 ones. Okay. But you can form 3 blocks here. Okay. You can form 3 blocks here. So let's say if we only take these 2 blocks here, okay, we cannot cover this one. Okay. But does it mean that we need to take these 3 blocks here? Okay. So we don't need to take these 3 blocks here because even if we remove the middle block, we still cover all the one. Okay. So this means that this means what? So we have the name for this. So these 3 guys we call prime implicant. But this 3, can you see the 3 or not? Okay, let me remove this one. So these 3 are what we call the prime implicant, and then only the outermost 2 we call the leg. Okay, only the outermost two we call the essential prime implicant. Okay. So what's the difference between them? So prime implicant, that means you are an implicant, but the block of one is not covered by a larger block. Okay. As long as you are not covered by a larger block, you are a prime implicant. Essential prime implicants, that means your block of one, this block of one is the only largest possible block that cover the one in the K-map. Okay. So let me show you. Okay. Something is not implicant, for example. Okay. So for example, if too messy now. Okay, if we have another big block covering the small block, okay, then this won't be the prime implicant. So prime implicant says that says what? Says this block is not contained in a larger block. Okay. It's not a larger block, represent the product of fewer literals. So for example, okay, we don't need to care about this. Because if you want to cover the one, you also can draw like this. Okay. You also can draw okay. So maybe too many picture you confuse again. So let me redraw this. Okay, one simple idea is if you want to cover the one, okay, why not you just draw like this? Okay, this also can cover the one. Okay, why not we draw this? Okay. Because we want to use the fewer blocks with larger blocks. Okay. So that's why we consider the 2 times 1 block in this case. Okay. So in this case, the smaller one, okay, maybe use different color. So in this case, the 1 times 1 block is not prime. So only the blue one are prime implicants. Okay. Okay. But you can see that you can see that you can see that you can see that what color should I use? Okay, let's say we pick up the 2 pink block. Okay. But you can see that this 2 pink blocks here, okay, is the only largest possible block of one covering one in the K-map. Okay. So you can see that this 2 pink block here is the largest block that covering one, this one. Okay. Although this one here is get covered by other blocks, but this one here only covered by this pink block. So that's why we call the pink one essential. Okay. So to simplify the circuit, we only care about essential prime implicants. Okay. Essential prime implicants will help you to cover all the one. Okay, make sense? Because it's the only largest block that cover one. The only one. So you need to take it to cover all the ones inside your K-map. Make sense? Okay. So you care about essential prime. Okay. So come back to the example here. So we just need to care about these 2 blocks here. Okay. So what's this block simplify to? What's the implicant of this? They differ in y, so they reduce to xz bar. And then how about this? They differ in z, so they combine to x bar, y bar. Okay. So 4 terms become 2 terms. Okay. Any question? How to see prime implicance? Okay. So prime implicance, let's go back to example again, definition. So prime implicance says that if this block of 1 is not contained in a larger block of x, ones, okay? If this block of ones, okay, is not contained in a larger block of 1, okay? So you can see that the the huh? You know? Wow, suddenly no. Huh? Yeah. Block have to be 2 to the power n times 2 to the power n. Okay. You can only form blocks of 2 to the power n times 2 to the power n. Yeah. Yeah. Yes. Yes. Even though you swap it also can because we don't care. Yeah. Okay. 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 So for 4 variables, you will need 2 to the power 4 cells so that you have 16 cells. Okay. And then 16 cells. 16 cells. What? Okay. So 16 cells, you can imagine you have more ways to combine the cell. Okay. You can see that this corner are also adjacent to each other. Okay. So you can imagine if you have five variables, 6 variables, 5 variables, you need 32 cells. 6 variable, you need 64 cells. And then 180, 28 cells. Okay. So you're getting more and more and more and more and more. And more. Okay. So it will be getting harder. Okay. So this is an example of simplifying 4 cells. Huh? What? Okay. Huh? Okay. Um. So um. So because when you're getting more cell, it will get harder and harder. So we'll introduce another method to calculate called the Queen-McCluskey method. Okay. For n greater than 4 cell, maybe it's easier to use this than to draw the big cell. Okay. So what you do here is you get your function, okay, you have your min term, and then you represent the min term using big string, using 1 or 0. Okay. You use 1 if xi occur. You use 0 if xi bar occur. Okay. 1 for x bar, xi bar, the complement use 0. And then the next step, you try to combine all the products in n minus 1 variables. Okay. So that means you reduce all the adjacent cell. Okay. You reduce all the adjacent cell first. And then after you reduce, you will put 1 again if xi occur, 0 if xi bar occur, and dash for the literal that you already get simplified. Okay. And then you keep doing this for n minus 2, n minus 3, adjacent cell, keep going each step by each step. And then you find all the Boolean product that used to form the product. That enough to cover your min term. And then you find the smallest set of them. Okay, let's look at this example here. Okay, let's look at example here. So for example, you are given this function here, okay, fxyz, okay. Fxyz contain 1, 2, 3, 4, 5. 5 min term here. Okay, so you list down the min term first. Okay, and then you turn this min term into a big string. So x, y, z, you will put 1 for x, put 1 for y, and put 1 for z. And then put 1 for x, 0 for y bar, and then 1 for z. Okay, and then so on. So you produce the list of big string here. Okay, then the first step is to find adjacent cell. Okay, for example, 1 and 2. Okay, 1 and 2, they are differ in exactly 1 literal. So you can combine y and y bar. So you're left with xz. So when y bar get cancelled, you put a dash. Okay. Okay, next, you can see that 1, 3 are also adjacent. Okay. So they differ in x. X it can be combined. So at the end, you get yz. Okay, so x get cancelled, you put a dash. And then you can combine 2, 4, 3, 4, and then 4, 5 together. Okay. So next, you can keep checking whether they are adjacent cell or not. So for example, you can check that actually these 4 are adjacent. So they can be combined to z again. Okay. So this 4, what do we have here? We have xz, yz, y bar z, and x bar z. Okay. So this one can be combined to just z plus y bar z. Where you get? Is it too many? I think we shouldn't add them together. Should we add them together? Hmm? Can. Okay. Seems okay. Okay. I believe you. So you get 1 plus 1 is that? 1 plus 1 is not 2. 1 plus 1 is 1. 1 plus 1 is 1. Right? Is that right? Yeah. 1 plus 1 is 1. Okay. Yeah, 1 plus 1 is 1. Okay. Yeah. It's 2, then we wrong. Okay, so yeah, you should tell your friend 1 plus 1 is not 2. Yeah. Okay. Yeah, get Z. So you can see that you see 1, 2, 3, 4 here. This one, don't be confused by 1, 2, 3, 4 here. This 1, 2, 3, 4 actually come from here. Okay. It turns out that this first 4 here is produced by 1, 2, 3, and 4. Can see it? Okay. So when you go to your textbook and refer this number, right? This number actually refer to the number here. Okay. So don't be confused by the position here. It turns out that this 4 here is made up by 1, 2, 3, and 4. Okay. So the next step here is to find all the Boolean product that arose that were not used to form a Boolean product in one fewer literal. Okay. So that means you can see that these mean term here are used to form the implicants here. Okay. So we don't want this. And then this 4 here, okay, let me just point it out. To build this. And then this 4 here are used to build this Z. Okay. So we only care about the unused implicant or the unused mean term. Okay. So how should I highlight it? So we only care about Z and X bar Y bar. They are the essential prime implicant. They are the essential prime implicant. They are the essential prime. Or they are the prime implicant. They are actually the prime implicant. The green one is the prime implicant because okay. So if you go back to the care map, right? Actually these 4 terms here. Yeah. Okay, actually this 4 term, where should I draw it? Okay. Actually these 4 terms here looks like this. draw like this. Feel like a bit misleading. A bit misleading. Okay, misleading. Okay, let me draw the 1, 2, 3, 4. So 1 is x, y, z. 2 is x, y, bar, z. Bar, z. And then x bar, y, z. And then x bar, y, z. Okay, so what's in the first step here? So the first step here is actually like this. Okay, it's all this combination. Okay, but go to this one is called step 1. Step 1. And then step 2 is actually the prime implicant. Okay. Prime. Okay, let me jump in a bit. So this one is the prime implicant, right? Because in step 1, the blocks is contained in a larger block. So they are not the prime implicant, but the yellow one is the prime implicant. Okay, this one gives the Z. Make sense or not? It makes sense. So what you do for this 4 step here, right, is actually you consider all the possible adjacent cell, 2 times 1 block. Okay. But we don't want this because we want the prime implicant or the essential. Yeah, both prime implicants, right? Correct or not? Yellow is also essential. I think yellow, yeah, yellow is essential as well. Wait. Yeah, correct. Yellow is essential. Yep. The green. Which one? You mean this one? S bar Y bar? Yeah. This one is essential. I didn't draw it out. I just point out this part here. I didn't draw for this. I haven't drawn for this. What's this? Oh yeah. Green are essential. Yeah, green are essential. I mean, yeah, green are essential. I mean, this part here, I think is more. This green here is more direct to see. Okay, because why? Because this one, where should it appear? It should appear. Let me see. Where should it appear? Let me see. Let me see. Wait. Let me check. Where should this guy appear? This guy should appear on the left. Okay. How should I move this? Let me add one more. Okay, then move this down. Okay, so how about the second green one? So where's the second green one? Okay, so the second green one in the K-map should appear on the right. Okay, so this part here is for the X bar, Y bar. Okay, so both of these are essential prime implicant as well. Okay, make sense? Okay. 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 How about the rest? Yeah, you need the essential prime to cover it. Okay. Then you can form a table. So you can list out the mean term of your function, and then you list out your implicant. Okay. If your implicants cover the mean term, you put across. Okay. And then you take the smallest set of the implicants that cover all the mean term. Okay. So why is this important here? Because you might have more prime implicants that cover more implicant that cover the same midterm. Okay. So for example, in this case here, okay, so let's not run through how to get the implicants, but let's see what's the end product we get here. Okay. So in this case here, all the midterm are get to produce the implicant in the step one, and then the last four implicants here are used to produce the step two essential prime implicants. So now you're left with four implicants to cover your function. Okay. So in this case here, the first essential prime implicants cover 1, 2, 3, 4. Four midterms here. Okay. And the second essential prime implicants here cover the first and the fourth midterm. So you only left with the second midterm here. Okay. But you can see that both of these cover the second midterm. Okay. So that means you can pick either one of them. It's enough. Okay. You don't need to pick all of them to cover the midterm. Okay. There are extra implicants here. Okay. So the final answer is either W bar Z plus WYZ bar plus WS bar Y, or WZ bar, W bar Z, WYX bar plus X bar YZ. Okay. So you need to pick the smallest set that can cover your function. Okay. So you can see that this is the product or the sum of 7 products of 4 literals become a 3 sum of at most 3 products. Okay. Yeah. What? Hang. Okay. Any more question before we have a break? No. Okay, let's come back at 10:57. Okay. And prepare for quiz. Where's my attendance list? Attendance. Hello, hello. Okay, we need to wait for another student for DMT before we start. So someone say want to watch the part two. Part two. But part two, I don't know how much of you can understand because more Malay inside. Okay, now is the time to test your Malay class. More Malay inside now, so I'm not sure how many of you will understand. So part one says the Australia prof say Malaysian don't think. Okay. Iam Tudor is like shut up and sit down. So I say during the primary school, if you ask teacher, what do you think? Teacher asks you shut up and sit down. Yeah. So yeah. Huh? What? Okay, watch this one again. Watch until. Huh? Which one? I think this one less joke in Instagram. What's this? No lah, this one got joke meh? No lah, this one is just video. This one ah. Let me try. Ah, what do you want to watch? My homepage got nothing on. Ah, this one ah. Classic. Ah, this one. Okay. Bodoh is still big in Malay. Okay, I think the student should be here soon. Four, four. No, I think we have 30 minutes. 30. One is today one. Huh? Now 6. Yeah, I think she is coming soon on the way. Traffic jam. On the way. Okay, let's split into 4 groups. 1, 2, 3, 4. Okay, count the first person. Please help me to count how many in your row, and then come and collect the test paper. Thank you. Okay, you can read first. Don't start yet. Oh. Yeah. Okay. Okay. Wait, everyone get the exam first. Get the paper first. Hmm? Everyone got it yet? Just turn on the light. Okay, so first page, you have 10 marks. And then second page, you have 10 marks. But second page have bonus question. So the bonus question only add up to the second page. Okay. So bonus won't add to the first page. Okay, makes sense. Makes sense? Okay. So we have a final quiz for the semester. So let's start 1108. Let's end at after 30 minutes. 1138. Okay, you can start now. Make sure you explain, don't just write yes or no, because there are 2 marks. Done. Clean up your solution. Check if you have the name and student ID. Okay, can pass the solution from the back to the front now. Please pass your solution answer to the front. Hmm. Pass your solution to the front. Hey, second rows, where's your solution? Second row and third row, sir. That means second row, third row.